So today we're going to talk about the second type of chi-squared test. The one that we did was chi-squared goodness of fit. And so let's first kind of review that real quickly so that we know how to compare that to what we're doing right now. So when we did chi-squared goodness of fit tests, we had claimed percentages for each type of item in a particular category. We had a claimed percent, and so then that helped us to know what the expected counts were. Okay, we did those in columns because we just had one category, one variable. Okay, and so then we had the counts, and then we had the expected counts. So we had two lists, counts and your expected counts. All right. This next item that we're going to do is called the chi-squared test of homogeneity. And so that's accented right there on the EI. So homogeneity is how you say that. And we know homogeneous is the same. So homogeneity is typically happening when we wonder if two or more groups have the same distribution of counts. For example, you wonder if senior adults, middle-aged adults, and young adults drink milk at the same rate. Now, if this problem did not have this third column, then I could get one proportion from drinking milk out of the total, and the second proportion from drinking milk out of the total, and I would have two proportions, and I could compare the proportion of senior adults that drink milk to the proportion of middle-aged adults. What kind of test would that be called if I just compared two proportions? Two proportion z-test. Very good. Okay, however, in this case, I have a third category. So since I have a third group, then, I've got this proportion here. I've got multiple proportions, and I can't then just do a two proportion z-test. That's when chi-squared test of homogeneity comes into play. So these do not give me claimed percentages like the chi-squared number, or goodness of fit, chi-squared goodness of fit. All right. So again, we want to compare those types to see if they are happening at the same rate. Here is one other example. What if we were wondering whether or not regular M&Ms, peanut butter M&Ms, and peanut M&Ms have brown M&Ms at the same rate? We don't do all the colors. We would just do one particular color, so we would have brown and not brown. Doing all the colors, brown, red, yellow, and having more brown, red, yellow, blue, green, and so on, that would happen. We're going to talk about that tomorrow. That's the third kind of test. But just one particular item across those three groups is the chi-squared test of homogeneity. Now, let's talk about what's different in this for assumptions and conditions. Random will be the same. Independent, as far as in the sample size, is less than 10% of the population for each respective group population. But let me ask you this. Do you recall when we had two proportions, if we were comparing one proportion to another proportion, what was another condition we had for independence if we were just comparing these two groups? What else did we say in our conditions? Good, that those two groups are independent of each other. So that will still hold even when we have three groups. So that is this item right here. The groups are independent of each other no matter how many you have, 2, 3, 4, whatever. All of those groups are independent. All right, our large enough will also be the same. What is large enough? There's a count greater than 5. What kind of count? Expected count greater than 5, and you have to make sure you got that down. But look, since this is multiple dimensions, not just one column into list 1 that we have for our data. It's multiple dimensions. It has, then our degrees of freedom are based on both dimensions. Rows minus 1 times columns minus 1. Okay, so that's a new way to do degrees of freedom. Rows minus 1 times columns minus 1. So there we go. So that's the two assumptions and conditions things that are different for these than our goodness of fit. All right, moving on. Now, up at the top of the next page is all the steps of how to do this in your calculator. We're not going to do that right this second, but when we get to it, I just want you to know that all your calculator steps are listed right here, so you won't have to write them down when we do those. Now, let's talk about how to get expected counts. When we had our chi-squared goodness of fit, let's look back at a chi-squared goodness of fit test. So say when we had that, how did we get these expected counts on a chi-squared goodness of fit? Good. We multiplied the percentage that was claimed times the total sample size, and that's what gave us our expected value, and we did that for each category. So our claimed percentage times the sample size, that gave us our number there. Well, this is going to be computed differently since we have multiple dimensions. So let's go over how that's going to work. I'll just show you this right here, and then we'll do that later to let it solidify. But we will be multiplying the row total times the column total, and we will be dividing that by the entire total of the set. So when we get to that, that's the formula I'm going to be referring back to. So let's practice this and do this problem. Here we go. It is common folk wisdom that drinking cranberry juice can help prevent urinary tract infections in women. In 2001, the British Medical Journal reported the results of a Finnish study in which 3 groups of 50 women were monitored for these infections over a 6-month period. One group drank cranberry juice daily. One group drank the lactobacillus drink daily. Now, a lactobacillus drink, that's like Activia or like a probiotic type thing, maybe even Go-Gurts. I wonder if that would count. Probably some kind of, like Yakult. Have you ever seen those little things, Yakult, that you drink? Anyway, so a lactobacillus drink. And then the third group drank neither of those beverages and served as the control. In the control group, and now it gives the results. 18 had at least one UTI, 20 of the lactobacillus, and 8 of the cranberry juice. Does this study provide supporting evidence that these 3 groups experience urinary tract infections at the same rate? So that will be our primary question. Additionally, later, I'm going to show you how we can address something that's a more specific question, such as this. Additionally, does this study provide supporting evidence for the value of cranberry juice in warding off urinary tract infections? But initially, what is our null hypothesis for this problem? Good, that all 3 treatments, and I'm not going to clarify those right out. I would, if this was, say, the AP exam or a test, I would write out cranberry juice and lactobacillus and da-da-da-da. So I'm going to put all 3 treatment groups result in urinary tract infections at the same rate. Okay. All right, so see if you have evidence of the alternative or not, which would say what? Okay. Do not result in UTIs at the same rate. Or you could say they have results at a different rate or something like that. Okay? All right, so there's our null and our alternative. We're going to see what kind of conclusion we make from our sample we got. So now let's do our assumptions and our conditions. All right, random. How are we going to address that here? Random what? Aha, good. Every class period, I have had somebody make that connection that this is an experiment and we are randomly assigning the women to the treatment groups. Very good. So we know that we are randomly assign women to the 3 treatment groups. And I guess that's assumed because it doesn't say it. Okay. All right, how about independent? Okay, so I'm going to do this per group, okay, because this is, multiple groups. So technically it's 50 is less than 10% of all the women in the cranberry juice group, and 50 is less than 10% of all women in the lactobacillus group, and 50 is less than blah, blah, blah. So for all 3 groups, luckily they're the same number. 50 is less than 10% of their respective treatments groups, respective populations, I guess. I would probably, I don't know, let's see. Okay, and what else do I need to say about that? Good. Groups are independent of each other. So nobody's in multiple groups. Okay, and last but not least, are large enough. So what's going on there? What needs to happen? All of the expected counts need to be greater than 5. So, we need to go find those expected counts and how much those are. Okay, so now comes some math. Go to the top of the next page where we see I've got this ready for us. We do not just have one column of observed and one column of expected. We now have two-dimensional matrix of observed and a matrix of expected. Yippee! Okay, so that you don't have to flip back to the other page, let me go ahead and tell you what the data was. Our control, 18 developed UTI, 20, and 8, which since these all totaled 50, you can fill in the blank of what's missing. Okay, I'm also going to need the row totals. Those are 46 and 104. All right, so that's the observed. That's what we got with our sample. So let's look at our expected. So I'm going to show you this by hand. Calculator can give that to us, but we can't depend just on that because I have seen problems where based on the data you have been given, you have to know how to do it by hand. Just doing it in the they don't give you enough information to do it in the calculator. All right, so let's talk about what this would be. To find the expected for this particular cell, which corresponds with this particular cell in the observed, it's going to be my row total times column total over total. Okay? So let's put some math to it. For that cell, what is the row total? Good, 46 times the column total, 50, divided by the total, 150. That number is 15.3. Okay? Now, I'm going to tell you that it's unusual that we actually have 50 in every single one of these here. A lot of times those will be different numbers. But it makes it simple for us because if there's the same amount of women in each group, then their ratio is the same. So this is also the same. Please do not think that will happen all of the time. That is only the same because all of the women had 50 in it. See, each group had 1/3 of the total. So that's why each expect. So out of the 46, you expect 1/3 in each group to be in each of those things. Now, I need these to add up to 50 in each column. So this is going to be 34.7. But of course, if you don't catch that, you're welcome to again do row total times column total divided by the total. Okay? Because we have the same number of women in each group, there's that. Okay, questions there. So, why did we jump over here to do the expected numbers? What am I supposed to look at and recognize from this expected matrix? All of these numbers in this expected matrix are bigger than 5. So that is how I finish out this. That was kind of like a side step we had. So large enough. As you can see from the expected matrix, all expected counts, if you don't put the word expected there, I would mark it wrong, because I think if you only put the word counts, that's ambiguous as to what kind of counts, observed counts or expected counts. All expected counts are greater than 5. So, with that being the case, what model applies? Not normal, not nearly normal. Chi-squared model applies. All right, very good. So, what's the name of this test that we're going to use? Chi-squared test of homogeneity. Chi-squared test of homogeneity. Okay. Now it wants the test statistic and the p-value, the degrees of freedom. So we're going to go to the calculator to get that. So everybody, calculator up. Let me show you how to do that. Here we go. We do not go to the list because this data is multidimensional. We go to the matrix. So you need to go second matrix, which is the x to the -1 button. Second matrix. And I'm going to go over to edit and hit enter. Okay. So in that matrix, so then yours is a different size probably showing than mine. I can never remember which number's row and which is column. I just play around with the numbers 2 and 3 until I get the one that's the same size as the one I've got. So it is a 2 by 3. So what you need to do then is put in these numbers that you got. Your 8, 20, 18, 42, 30, and 32. Okay. So that makes your observed matrix. Now, the nice thing about the calculator is computing the chi-squared test will make the expected matrix for you. Since it's a formula, it'll go ahead and make that for you. So we do not have to put in the expected matrix into another matrix. We don't have to put anything else in. So let's go run the test. Stat, over to test, go up, not the chi-squared GOF, the chi-squared test. Okay? Observed is matrix A. It is telling you it's going to compute and put in matrix B the expected. And so then now I'm going to go down here and calculate. And voila, there is my chi-squared, my p-value, and my degrees of freedom. So my chi-squared is 7.78. My p-value is 0.02, and degrees of freedom, 2. And so the next page is where we will make our conclusion and everything. So what will I compare to alpha? Good. My p-value of 0.02 is less than my alpha of 0.05 since they didn't give that to me. So since my p-value is low, what am I going to do? We're going to reject HO. So what I need to do to conclude is I say since 0.02 is less than 0.05, I reject that. Okay. And at this point, I want to take just a moment and have your brain think about this, because this is where I sometimes get people putting the wrong thing here. Okay? So you're rejecting HO. What does HO say? Are you rejecting that the rates are the same or that the rates are different? Same is what HO says. You were rejecting HO, which says they are all the same. So make sure that's what you are writing here. I reject that the 3 groups get UTIs at the same rate. Now, if this were a test or a AP exam, you'd want to be very thorough and say, I have evidence that, and then put whatever your HA says. You know that they are doing things at a different rate. They're doing urinary having, okay? But it's really kind of redundant. Okay. Now, one last thing to teach you. Questions there so far? Okay. One last thing to teach you, and this happens because you may be asked a more specific question. If you're just asking about the collective decision to make about if they have the same rate or not, that's a test like this. But this takes one more question and asks you about cranberry juice particularly. So in order to do that, we're going to look at this thing called standardized residuals. So at the bottom of this next page, we're going to look at these standardized residuals for each cell, each little component in our matrix. Now let's review what a residual is. We've done it when we did linear model stuff. So if this is the expected data, and this is an observed piece of data, where's the residual? Okay, good. It's this distance here. And is this a positive or a negative residual? It's a negative residual. So if your observed is below what was expected, you had a negative residual. Okay? And if your observed is above what's expected, you have a what? A positive residual. Okay, so keep that, that's a little residual refresher. And so what we're going to do is for each cell in our matrix, we're going to get this thing called a standardized residual. It is this formula, observed minus expected over square root of expected. So I keep throwing all these formulas. This is not on the formula chart. However, I have a way for you to remember it. And so here is the way that I think you can remember this. If you take a look here at the chi-squared formula, okay, here's our chi-squared formula. Observed minus expected, quantity squared over expected. If you think about just like doing a blanket square rooting it, it's technically not mathematically correct because that involves many more like FOIL and all this kind of stuff. But if you think about unsquaring the top, no square, and square rooting the bottom, that is your formula for your standardized residuals. Okay, so maybe that can help you remember it. If you just think it's the square roots of those things, in a sense. I hate to, especially since I'm recorded, I hate to mathematically say, oh, it's just the square root of that, because mathematically that's not entirely correct. But that could help you remember it. So let's do that. And so up here at the top of the next page, I've got yourself a little thing here ready to go. And so for each one of these cells, you're going to have to do the computing. Luckily, there's only 6. So let's talk about this one particular cell right here. All right, so how many observed urinary tract infections were there for the control group? There were 18 urinary tract infections observed. How many did we say were expected to happen when we did our expected matrix? 15.3. And then I put it over the square root of that expected number, and that is how you get that value right there. Okay? And then you would do it for each cell. Do that formula for each cell. So I have that done so you don't have to go do all that math and waste your time doing that. It's more about interpretation than doing that simple computing. So here comes that. Okay, so take a look right here. There are the computed standardized residuals for you, already done. And so after you write those in there, we want to interpret what is going on. See, you notice some of them are negative, some of them are positive. Some of them are bigger numbers. The bigger the number, what can you say? The farther away it is from expected, okay, in both directions, okay, the bigger the magnitude. Okay, so our question said, additionally, make a comment about the benefits of cranberry juice in warding off urinary tract infections. So what can you say about cranberry juice and urinary tract infections? Yes, the fact that this is negative is indicating that it is happening less than expected. Yeah, and then look at these two guys right here. Both of these are positive. So both the lactobacillus and the control are getting urinary tract infections at a higher rate. Furthermore, which is worse of those two? The higher one, which is the lactobacillus group. Yeah, so do you see how doing the standardized residuals lets you get more detailed information about each component, okay? So here is what I wrote. I wrote 2 different sentences, but technically probably just the first sentence would answer the question they asked. You can see from the standardized residuals that women on cranberry juice get UTIs less than expected. Okay, that technically answers the question that was asked. So it could be that you may not have to do all the standardized residuals, but I still would expect you to. I think you need to compare, what were the other ones doing. So I put additionally on this, cranberry juice got UTIs less than expected, while the women in the lactobacillus and control groups got UTIs at higher than expected rate. Okay? All right, so what I'm going to have you do for homework, actually, which most people have been able to finish this in class, is all the way over, you skip some notes, and you go over to page 17 in your packet, and I will walk around and answer questions and help you during class for you to do that.